Hello, welcome everyone to Physics Live with Ankan Bhattacharya. And you are known to the fact that this is the lecture series of nanomaterials and applications, where the development of nanomaterials from the introduction has been achieved. And till now, what we have discussed is nothing but the introduction about the nanomaterial science. The next thing was the synthesis. The next succeeding thing was the characterization, and therefore we have discussed the various interesting properties of nanomaterials as compared to the bulk one. And now it is the time to discuss the applications of these nanomaterials. And throughout the entire lectures that has already been covered, I have emphasized on the nanomaterials due to the interesting properties that are discussed, but the main thing is to apply these interesting things in our daily life as well as to our desired purpose. It is the main reason behind the study of the nanomaterials. So this is the lecture which is the most important for the study of the nanomaterials, where the name of today's topic is the applications of nanomaterials. Okay, so the applications of nanomaterials. Now you are now in a position to understand what is nanomaterials. Let me revise you, or let me remind you that the nanomaterials are the materials that have one dimension, at least one dimension, at least one dimension that measures 100 nanometer or less. Okay, so many physical properties of the conventional materials changes when it is formed to be of the order of nano. This is said for many times throughout the entire lectures that I have already covered, but now I want to make you understand the physical reason behind the typicalness. Okay, physical reason for this typical behavior. What is the physical reason lying behind these exceptional features of the nanomaterials as compared to the bulk one? So the physical reason is attributed to the fact that the nanomaterials have the large surface area to volume ratio. This is the interesting thing which causes the nanoparticles to be more reactive to some other molecules and increases their inherent characteristics. Now let me make you understand how this feature involves some great importance here. Okay, let me show you. At first I want to draw a bulk material like this. Okay, this. Okay, so let us say that this is a bulk material whose bulk cubic material whose length is edge length is 1 meter length. Okay, so you can say that the surface area or total surface area is about let us say area total surface area is about 6 into 1 meter square means 6 meter square. Fine. Now let me divide this bulk material into some smaller components. So sorry. Okay, so let us divide the bulk materials, suppose by these fragments like this. Like this. As well as like this. So you can imagine that the bulk cubic uh, material is divided to some 1 2 3 4 5 6 7 8. So 8 compartments. It has been divided to 8 compartments. You can see by the division lines drawn in the figure. So let us suppose that this division is occurred by the equal side length. Okay, so this was half meter side length and this side length becomes sorry, this was 1 meter side length. So by equal division the two, let us say like this, the two half becomes half meter and half meter. Okay, so the each smaller cubic material have the side length of the order of half meter. Now the area becomes 6 into 8 into, sorry, for better understanding I must have to separately write this. So the area becomes um, 8. There are 8 compartments formed due to the division. So 8 into 6 of half meter square. This should be some whole square. So 4 into 2, that is 12 meter square. You can see that the equal division creates some increase in the surface area of the order of double. Similarly, if we divide the crystal by 3 equal divisions such as like this, like this, like this, like this. Okay, let me figure out the picture in a separate figure so that it will be better to understand. Okay, yes. So let us suppose that we divide this by 3 equal portions, each of side length 1 by 3 meter. Okay, so this is something like yes, and this will be divided like this. 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 And um, Okay, so now the each side length becomes of the order of 1 by 3 meter, 1 by 3 meter. So now the surface area becomes 6 into 1 by 3 whole square, and there are 27 compartments are formed due to this equal division. So 27 into this, so the area becomes 9 3 18 meters square. So you can see that by the division of 1 by 3 or 1/3 of the side length, the area becomes increased to 3 times of the bulk one. So this is the basic principle for the great difference in the physical properties when we reduce the bulk material to some smaller compartments. Okay, now nanometer order is very much essential or very much important, as because it has been observed by the experimental procedure. Okay, so let us move on to the fact that the application of the nanomaterials. So you have studied very uh, large variety of the nanomaterials, that are zero-dimensional nanomaterials like quantum dots, one-dimensional nanomaterials like nanowires, nano rods, nano films, etc. You have studied very well, and in this lecture I am going to discuss the applications of them separately. So at first, I want to make you understand that the nanowires and nanotubes, which have been derived as a one-dimensional nanomaterials, are very much important nowadays. Nanowires. Okay. By which reason it is very much important? As because they exist in many forms, that is made up of metals, semiconductors, insulators, and organic compounds as well, that are studied in electronics, energy conversion, energy conversion, optoelectronics, and chemical sensing. Okay, so nanowires are the one-dimensional nanomaterials that are very much important nowadays because of the application in electronics, energy conversion, optoelectronics means the optics plus electronics. So optoelectronics, chemical sensing, etc. Now the zero-dimensional nanomaterials such as quantum dots have immense applications. Quantum dots has immense application in medical purpose, display technology, solar cell, as well as uh, in chemical uh, synthesis, such as two synthesis electrodes. We will discuss later in great detail. This is something point of view, a little point of view about the different application in short form. Okay, so these are two important nanomaterials that are usually used in a very large amount in our recent times. Okay, so let us separate out each applications very effectively. Now at first I want to show you the applications of the nanoparticles in the medical purpose. So medical purpose application. as because the title of our article is application of nanomaterials, we have to explain the applications in different grounds of the whole nanomaterials. Okay, now the medical purpose is very much essential for our human being. Okay, in the medical purpose we can say that the nanomaterials are widely used for the treatment of the tumor or cancer cells. Okay, it is very much helpful in the treatment of tumor or cancer cells, and the use of polymeric micelle polymeric micelle nanoparticles delivers drugs to tumor. The next thing is important here is the use of polymer coated iron oxide helps to treat the traumatic injury. Okay, to treat the traumatic injury. Next thing is that uh, the nanoparticles that are made of carbons, which are known to be the diamond nanoparticles, are very much essential for nowadays because of its organic in nature. The core of the quantum dot is made up of organic materials such as carbon. That is why it is very much important. That is a diamond nanoparticle. Diamond nanoparticle is very much important for the researchers to use it in the chemotherapy drugs to treat the leukemia or skin cancer, etc. So these are some basic applications of the nanomaterials which are used in the medical purpose and which are very much important nowadays. The next thing is that we can apply the nanomaterials in the manufacturing of different materials like the ceramic silicon carbide can be dispersed in magnesium and it produces a strong lightweight material which helps to provide a barrier to the gases, which helps us in our protection of food or other kind of material from moisture. Okay, so this is important thing. And the next thing is that silver nanoparticle can be used to make the cloths bacteria and odor free. Okay, bacteria and odor resistant. This is the important application of silver nanoparticles. So the article is the application of nanomaterials in manufacturing and materials. The next Uh, the next thing is that the application of nanoparticles in the energy and electronics. In this regard, a very important thing I am going to show you, application of nanomaterials in energy and electronics. Okay. Researchers have found that the carbon nanoparticles, when developed to the nanotetrapods, which are usually effective for the to act as an electrodes and which can replace hugely by the high cost platinum electrodes, and so that the mechanism of the electrophoresis becomes very much cost effective. Okay, so what I want to make you understand is the thing that so we can use the carbon tetrapods to replace the high costing platinum electrode for the electrophoresis of the materials, and it uses or it increases the catalytic activity than the pure platinum, which helps in the process of the electrodeposition or cell catalysis. Okay, and researchers also developed the method of printing of conduction line inside the uh, breadboard or in the circuit board by the use of the silver nanoparticle, replacing the high price inkjet printers. Okay, so these are some applications of the nanoparticles in energy and electronics, and the more important thing is that we can manufacture the nanoparticle nanoparticle uh, organelle memory memory field effect transistor NOMFET by the application of these nanomaterials, which are very much helpful, and which acts as a great transistor, which is unusual in that it can function in a way similar to the synapses of the nervous system. You have studied in the biology what is the synapses of the nervous system. So the NOMFET acts like a synapses of the nervous system, and this is the main application behind the nanoparticles as an energy, as in energy and electronics. So next we have to move on to the specific nanomaterials to apply them in our modern day life. In this regard, the first thing is that the quantum dot, which is very much essential nowadays. Quantum dot. Now what is quantum dot? The quantum dots are referred to very teeny man-made semiconducting material or semiconductor particles whose size are normally no more than 10 nanometer. This small size renders the optical and electrical properties that I already covered in the previous lectures, that the small confinement within the material, that is a small size, makes a quantum confinement of the charged particles like electron, holes, etc., which results in some interesting properties in the optical as well as in electrical property, okay, as compared to those of the bulk materials. Now a majority of the quantum dots have the ability to emit light of specific wavelength if excited by light or electricity. And the interesting thing here is to point out the fact that we can tune this specific wavelength of light by changing the size, shape, arrangement, etc. of the components constituting the quantum dot. So we can say that it contains a variety of range of the visible light to infrared in the electromagnetic spectrum to emit the radiation, and this fact is used to the quantum dot solar cell. Okay, I will like to show you after some minutes. So here I want to only make you understand that quantum dots is very much important as because of this smaller size confinement, and it has the ability to emit the light of the specific wavelength if excited to light or electricity, and we can control this emitted wavelength by only changing the size, shape and arrangement. Now the interesting thing is how can we control, or what is the dependence of this size to the wavelength of light emitted. So let us draw some figure out here so that you will understand. Let us suppose this, sorry, okay, so let us draw some band structure. Okay, yes, so this is some band structure of bulk material where this is the valence band, this is the conduction band, and this is the band gap. If I plot the energy level through this, sorry, so energy is plotted along this, and the size is plotted along this. Now as suppose this is represent decrease in size, it has been observed experimentally that by decreasing the size you can easily understand why I am writing or why I am drawing this conduction band to be some discrete line and to some region of band, because it is derived from the band theory of solid, which I have already covered in the solid state lectures. So you will understand in a better way that how these discrete lines originate and this solid band is formed. So the lower one represent valence band The upper one represents conduction band, and this is some band gap between these two, and you can easily observe that the band gap increases by decreasing the size. Similarly, if the quantum dot has a size like this, suppose it is of the order of 10 nanometer. Now, sorry, I can draw the same thing in here, the same thing in here also, but you can observe the only difference in these graphs are the band gap increases as the size gets some decrease. This, let us suppose the size decrease from 10 nanometer to 6 nanometer, and from 6 nanometer to 3 nanometer. Okay, so by reducing or decrease in size, the band gap between the conduction band and valence band increases. Okay. So by changing or by controlling the size, we can achieve. One thing I have forgotten to discuss you, that the band gap is greater than as compared to this one, which was correspond to the bulk one. So when some electron is excited from valence band to the conduction band, and when this electron will make transition from the conduction band to valence band, it will release a greater amount of energy, which is equal to the band gap energy as compared to the this one. Similarly, when an electron is excited from this valence band to the conduction band and again back to this valence band, it will also emit energy which is obviously greater than the previous one. And we can say that by reducing the size, if an electron is excited to the conduction band and then the excitation is removed by the electron and back to the valence band, then the excitation energy which is removed by the electron will be greater when we decrease the size of the nanoparticles, as seen from the graph very well. So the energy increases as we decrease the size. So the wavelength decreases due to the increase in energy. The wavelength of emitted radiation decreases with the decrease in the size, so that the smaller size quantum dots emit the smaller wavelength. Smaller size quantum dots emit shorter wavelength. In visible regions such as blue, violet, green, etc. Whereas the larger quantum dot emit larger wavelength but longer wavelength, like orange, green, sorry, green I have written, orange, yellow, red, etc. So these things are to be noted. This makes the quantum dots as an attractive agent. Now we can constitute the LED, or we can form LED based upon the quantum dot layer. where the light emitting layer is comprising of the quantum dot is known as the quantum dot LED. Now it should be one question may ask in your mind that why we have made the quantum dot LED. What was the fault of the bulk LED that we ordinarily use? You can notice that by the advancement of the technology, our television size gets reduced day by day. When it was using a previously unmodified display technology, it was a greater in size, but as well as we form the liquid crystal display or light emitting diode as a display mechanism, then it becomes thinner day by day. So when we use the quantum dot layer in the LED, it has some basic superiority as compared to the previous LED. It has a wide range of emission wavelength, so that the light emitting by the quantum dot LED will be controlled by the size, by controlling the size, as well as the quantum dot LEDs are very much contain longer lifetime as compared to the normal LED, and the brightness of the picture is very much greater as compared to the normal LED in the quantum dot LED. Okay, so the quantum dots are being used to produce the miniaturized lasers also for the use of the communication devices. It is a great application of the quantum dot in the communication system, where we can use the quantum dot to produce a miniaturized lasers for their use in the communication devices. The advantage of these quantum dot lasers is that it has contained the high speed data transfer for low power consumption. Now I have not write the quantum dot LED, but discuss the quantum dot LED. So keep in mind that I have shown you some advantages, or I have told you some advantages regarding the quantum dot LED as compared to the normal LED, but there is some disadvantages. The main disadvantage is that the quantum dot LED manufacture is very much cost effective. It is not a simple task to manufacture the quantum dot LED. It is very much uh, contain high cost. So the costing is not so simple. And the next thing is that the quantum dots contain very toxic cores in between them. If I am going to show you the structure of the quantum dot, then you can understand in a better way what I am want to telling you. The quantum dot consists usually the three layers. The first layer is cores. This is core. The next layer is shell, and the last layer is So this is the complete figure. This is the surface binding ligand. Surface binding ligand. This is the shell and this is the core. This is the core. The core contains the actual very cytotoxic content like the cadmium uh, or higher order materials as the centers of the quantum dot. The next thing is that the shell is always required to protect the core region to get them detached from the environment, otherwise it becomes toxic in which medium it is kept. So shell gives us the separation of the core region from the external medium, and the surface binding ligand acts as the protective layer of the core and shell, and it helps in the passivation of the cell layer, which is very much essential. Now the surface binding ligand covers the surface defects and surface ions of the cells and thereby protects the quantum dot from the oxygen and moisture. So it is also important layer, and it is usually made from the oleic acid and olellaline. Okay, so these are the some things regarding the quantum dot structure. So you can put the heading as QD structure. Now let us move on to the quantum dot solar cell. Like the quantum dot LED has superiority over the normal LED, quantum dot solar cell also superior as compared to the normal solar cell. By which process? Okay, I can show you the structure of the quantum dot solar cell. For this, require some times. So let us draw the quantum dot solar cell. This is the last one. Now it is the time to name all the lines. Okay, so this layer is the transparent conducting electrode layer. Transparent conducting electrode. Conducting electrode, and this is the blocking layer. After the transparent conducting electrode layer, the blocking layer is produced, sorry, blocking layer is present or is produced, you can say. Okay, so this is the blocking layer. The next layer is the TiO2 film layer, titanium dioxide film layer. Next layer is the quantum dot layer. This is the quantum dot layer. This is the QD layer, such as lead sulfide, cadmium sulfide, etc. Then a layer is present this is the layer which can be known to be the hole or positive charge layer, where the positive charge are gets accumulated. And the next is counter electrode. Counter electrode layer. This is the main structure of quantum dot solar cell, QD solar cell. Okay, so let us try to discuss the working principle of it. Suppose when light enters into the transparent electrode of the quantum dot solar cell onto the light absorbing layer or blocking layer of the dots in order to generate the electron hole pairs, which are known to be the exciton. The charged particle then separate out eventually and travel to their respective electrode, that is the positive charge are, uh, gets accumulated to the this layer and the negative charge gets accumulated to this layer, so that the charge separation is happening there by the process of formation of electron hole pair. It then applied to the it then goes to the charge separation method, where the electrons and holes are get separated out and current conduction takes place. Okay, so in aqueous and UV condition, the degradation increases and the particles don't pass the high crystallinity seen in organically made quantum dots, but the process is easier, inexpensive, and more reproducible than the organic synthesis when we use this type of material as a quantum dot layer, like the Pb, lead sulfide, cadmium sulfide, etc. So the main thing is that, like in the normal solar cell, after the incidence of the light rays, like the photon particles, the excitons or the electron hole pairs are formed, uh, which are very much large in energy. Okay, but uh, the producibility of electron hole pair is very much low in the normal solar cell, but the producibility of electron hole pairs, although very small energies, is very much greater in the quantum dot solar cell. As well as in normal solar cell, the efficiency factor efficiency factor efficiency okay, put the topic quantum dot solar cell. Efficiency is, in normal solar cell, efficiency is about 33%. That is 33% of the incident light can be converted to the electricity, whereas in quantum dot solar cell we can get a efficiency of 65% approximately. Now the normal solar cell is comprising or is operated only to the visible region of light, but the quantum dot solar cell can uh, work with a wide range of incident radiation, like the infrared radiation. Up to the infrared radiation it can work, and we know that the radiation coming out from the sun is mostly infrared in nature, and by tunability of the size we can control, or we by controlling the size we can tune the incident wavelength uh, to work in the quantum dot solar cell. Again, the normal solar cell can only be used in the rooftops, whereas in quantum dot solar cell we can use it as in our windows. So these are some advantages of quantum dot solar cell, apart from the normal solar cell, where in quantum dot solar cell we use some quantum dot layer. Okay, quantum dot layer to operate the solar cell. But the main disadvantage, there lies some disadvantage, that is the surface defects is always present in the quantum dots, as I have already told you while discussing the structure of quantum dot. The surface defects can result in the blocking or temporary traps of the electron hole pair, and the origin of traps in the way surface treatment affect can the material, and the key factor is the distribution of well controlled elemental ratio. The electron will be happy when the distribution is just right, so that the conduction takes place in a proper way, but sometimes due to the presence of subsurface defects this is not possible, and we get some unwanted temporary traps, so that the efficiency gets decreased to some extent. Okay, and the trapping results in the blinking of the quantum dot, which deteriorate the quantum yield, that is the amount of radiation obtained or amount of energy obtained as compared to the incident radiation. The blinking effect can be reduced by having a small shell around the core that we have already discussed. That is why we have to use the shell above the core region. And I have already told you that the quantum dot band gap can be tuned by adjusting their size and composition. Okay. And the another disadvantage is the costing of the quantum dot solar cell is very much high as compared to the normal solar cell costing. Okay, and the core of the quantum dot is made out of the cadmium, which is shown in this figure. So cadmium, which is very much hazardous to our environment, but scientists are very much interested to replace these uh, kind of hazardous material by the organic material like carbon, but this is under our experiment. Next thing we have to discuss the nanowire application. I have already told you, but here I want to tell you what is nanowire, where the aspect ratio is very much nanowire. Nanowire is the nanomaterial where the aspect ratio is very much greater, even greater than 1000. Now what is aspect ratio? The length to diameter ratio of a nanomaterial is called the aspect ratio, which is very much greater as in case of the nanowire, and depending upon this aspect ratio we can classify nanowire, nanorod and nanofilm. The nanowires can be of the superconducting in nature like the YBCO, like the semiconducting silicon material, and it may be of insulator like SiO2, TiO2, etc. material. Okay, depending upon these four classes, superconductor, semiconductor and insulator, as well as metal, we can form different nanowires, different class of nanowires. And the nanowires are very much effective in the high speed data transfer, uh, storage devices in our computers, etc., and to form the NOMFET, that is the nanoparticle organelle field effect transistor, which is very much important for the modern day building element, fundamental building element of modern days electronic circuits. You know that transistor is very much important for producing some electronic circuits. So if nanowires can be applied, then the efficiency of the transistor increases and it can work with very much low power consumption. And the slenderness of the nanowires makes it very much interesting for the researchers. I think I have covered so many things in this lecture, so the next topics will be discussed in the next lecture. No more today. I want to, I do not want to make some burden on you. So I think this is enough for today, and the remaining portion will be discussed in the next lecture. Till then, you can read this topic from your textbook, and if you enjoyed this video, then you can press the thumb button for more updates. Thank you. It gives some mere motivation to me. Okay, goodbye.